What if the deadliest stars aren't black holes, but iron cores that refuse to die? In the heart of a collapsed star, densities crush protons and neutrons into a soup where quarks break free. The astonishing fact isn't that a star can clamp a few solar masses into a sphere the size of a city, but that something inside might harden against gravity at the moment you'd expect it to surrender. If you glimpse this physics, collapse isn't a one-way street. There could be a phase of matter so stiff that it holds the star up, even as gravity gnaws away. This is the mystery of quark matter in neutron stars, where a tiny phase change at the core can stop a collapse that seems inevitable. How does that phase arise? And what does it demand of space, time, and particles themselves? Stay with me, curious minds. Before naming the phase, we need the stage. Physicists built neutron stars from gravity, quantum mechanics, and the idea that matter resists being squeezed into smaller volumes. The classic picture treats the core as a dense nuclear liquid, where protons and neutrons push back with a pressure set by the strong force. Gravity should win unless the pressure stays stiff. The first big question: at what density does a new form of matter appear? In the 1970s and 80s, theorists asked whether hadrons could melt into deconfined quarks inside a star's core. Early models, like the bag model, suggested quark matter could exist, but the consequences were unclear. A quark phase might soften the equation of state, making collapse easier, or, surprisingly, could stiffen it through new interactions between quarks. Observations then pressed the mystery into view. Two solar mass pulsars showed neutron stars can be compact, demanding a stiff core. If quark matter exists and softens the EOS, these giants would be unstable. So researchers explored how quarks could pair up, how repulsive forces between quarks could resist compression, and how a possible transition could occur without destroying the star's integrity. The landscape shifted with improved data. Tidal signals from mergers and measurements of radii with X-ray missions began to map which cores are plausible. In short, the question isn't whether quarks exist in stars, but what phase they occupy, and how that phase shapes stability under gravity. This is the backdrop for the mystery of whether a quark matter phase can halt collapse rather than hasten it. Now the core piece. When matter is squeezed to densities higher than nuclear saturation, a phase transition can flip the script. Hadrons melt, and quarks roam in a sea that behaves differently from nucleons. The key questions are: what phase is it, and how does it resist gravity? A popular model uses deconfined up, down, and strange quarks to form quark matter. In some versions, quarks pair in a color superconducting state, where pairs of quarks lock together like electrons in a superconductor. The pairing gap acts as a quantum glue, making the matter less compressible at high density. But the magic is in the interactions. Repulsive forces between quarks, encoded as a vector coupling, push back against compression. That extra push stiffens the equation of state, so doubling the density doesn't produce a proportional explosion of pressure, and collapse becomes harder rather than easier. Imagine a crowded elevator. As more people cram in, the floor doesn't sag as much if there's a hard, shared rhythm that resists squeezing. In neutron stars, that rhythm is quark-quark interaction. A vector repulsion acts like a steel beam, distributing pressure across the core rather than letting gravity pile up weight locally. The phase boundary might be a smooth crossover or a mixed region where hadrons and quarks coexist. In some narratives, the transition is abrupt and creates a softer segment. In others, a continuous, stiff path keeps the star safe. The interior might host a shell of confined matter, giving way to a mixed phase that becomes pure quark matter in the deepest core. The exact arrangement matters for stars' mass-radius relation and for how mergers deform it. Evidence is indirect, but the logic is tight. A stiff quark core can hold back collapse, while a soft one would send the star toward a black hole. The search continues with nuclear theory, lattice QCD insights at high density, and multi-messenger astronomy providing clues about hidden phases inside these iron titans. Why does this matter beyond a physics textbook? Because the interior of neutron stars is a lab for matter at densities Earth cannot reach. If quark matter can be stable at core pressures, it changes how we interpret mass, radius, and tides in mergers as clues about QCD. The existence of a stiff quark core helps explain why some neutron stars survive with two solar masses, while others merge and radiate gravitational waves. It also fuels the idea of strange quark matter, forming stable, self-bound objects with different surfaces and flavors. More broadly, this research pushes the frontiers of phase transitions under extreme conditions. The boundary between confined and deconfined matter may be smoother than once thought, or it may hide a sequence of layers. The outcome matters for astrophysical models, for NICER's radius measurements, and for linking celestial observations to collider experiments that recreate hot, dense matter in miniature. In the larger map of reality, the story of quark matter in stars reminds us that nature can assemble everyday ingredients into extraordinary phases that bend the rules we thought fixed. It invites us to trust the evidence, not intuition, and to listen for the next observation that could rewrite the interior of the universe's densest objects. Every data point tightens the fabric of our cosmic understanding. Let's recap the thread. From a stubborn question about how matter behaves under crushing gravity, we arrived at a tale of phases, pairing, and a star that defies expectation. The iron heart of a neutron star might be filled not with quiet neutrons, but with quark matter that glues itself together through color superconductivity and stiff repulsion. The result is a cosmos where collapse can be arrested not by luck, but by quantum choreography at unimaginably small scales. If true, this changes our sense of what's possible in the universe. States of matter that resist gravity more than once thought, and the deep unity between the physics of tiny particles and the fate of giant stars. The next generation of telescopes and detectors will test these ideas, turning speculations into measurements. The stars themselves are not silent. They whisper the rules of reality to any curious listener. If you want more, subscribe now.